So hello everyone, welcome to another video on discrete maths. We were doing this topic called relation, and let us continue with that. In this particular video, we are going to look at a special kind of relation. It is called equivalence relation. Alright, so let us look at the definition of equivalence relation. Okay, a relation on a set A is called an equivalence relation if the relation satisfies a few properties. Alright, so what are the properties that are needed to be satisfied? The relation has to be reflexive, it has to be symmetric, and it has to be transitive. Okay, so a relation, if that relation is reflexive, symmetric, and transitive, then that kind of relation is called a equivalence relation. Alright, now let us say some ordered pair AB belongs to this relation R, and let us say this relation R satisfies reflexive, symmetric, and transitive property. That means this relation R is an equivalent relation. In that case, we will say that A is equivalent to B. Alright, and this is denoted using this symbol. A is equivalent to B. Alright, so let us talk about this equivalent relation using this operation called equal. Okay, this equal operation. Let us say I have this relation R. Okay, I am defining this relation R such that it will have this AB if A is equal to B. Okay, so let us think about this relation, equal relation. All this A is equal to A, B is equal to B, 1 is equal to 1, 2 is equal to 2, 3 is equal to 3. So all these AA pairs will belong to the relation, right? So because of this we know that the relation is symmetric because A is equal to A, B is equal to B, and so on. Alright, now I know if A is equal to B, then B is equal to A. Okay, so if AB belongs to the relation, then BA belongs to the relation. Alright, so because of this I know that the relation is symmetric. Now if A is equal to B and B is equal to C, then I know that A is equal to C, right? These are from basics of arithmetic, right? So if A is equal to B and B is equal to C, then A is equal to C. So if AB is in the relation and BC is in the relation, then AC will be in the relation. So we know this relation is transitive, right? So all this reflexive, symmetric, and transitive, these three properties are satisfied by this relation, right? So this relation, we will say this is a equivalence relation. Now don't confuse this equality, this equal operation with equivalence relation. We will see other relations that are not this equal operation, but they are also reflexive. So let us start looking at this with examples. Okay, let us first talk about this relation. This one we have already seen. This relation AB, this relation R will contain this ordered pair AB if A is equal to B or A is equal to minus B. Okay, so in this relation, is it reflexive? We will have to figure it out. Is it symmetric? And is it transitive? Alright, three things we have to figure out. Is it reflexive? First thing. So all this A is equal to A, B is equal to B, C is equal to C. So all this 1 is equal to 1. This relation, of course, I did not specify what is the set on which this relation is acting, right? So this relation R is on the set of, say, integers. Alright. So this is on the set of integer. So all this 1 is equal to 1, 2 is equal to 2, 3 is equal to 3. So all these ordered pairs 1, 1, 2, 2, 3, 3. This will exist in the relation. Alright, because of this condition. So it is reflexive. This 1, 1, 2, 2, 3, 3, all those will exist in the relation. Is it symmetric? So it may happen that x is equal to y. If x is equal to y, then y should be equal to x. Okay? Then if xy belongs, then yx should also belong. Since x is equal to y implies y is equal to x, that means xy being in the relation means yx is in the relation. Similarly, if x equal to minus y, because of this, if x equal to minus y, that means x minus y belongs to the relation, then y is equal to minus x. Correct? If x is equal to minus y, then y is equal to minus x. This is from arithmetic. So I have seen that if x minus y belongs, then y minus x also belongs. That or minus y x also belongs. Right? Sorry, it should be minus y x. If x is equal to minus y, then minus y should be equal to x. Right? So all these things will belong. Right? If some AB belongs, then it implies that this BA also belongs to the relation. If 1 minus 1 belongs, then minus 1 1 also belongs. Okay. Anyway, this is the same thing. This is 1 equal to minus of minus 1. So 1 minus 1 will belong, right? And minus 1 is equal to minus 1. So minus 1 1 will also belong. So because of this we know this is symmetric. Is it transitive? Now there are 4 cases that may arise. Okay. Let us look at the 4 cases. X equal to y and y equal to z may be one case. X equal to y and y equal to minus z may be one case. X equal to minus y and y equal to z might be another case. X equal to minus y and y equal to minus z. This might be another case. Alright. So if x is equal to y and y is equal to z, then x is equal to z. Okay. If x is equal to y and y is equal to minus z, then x is equal to minus z. Alright. If x is equal to minus y and y is equal to z, then x is equal to minus z. Similarly, x is equal to y minus y and y is equal to minus z, then x is equal to z. Okay. These are something that we got by arithmetic. Now, if this and this belongs, okay, xy and yz belongs to the relation, then will xz belong to the relation? Yes, xy and yz belongs to the relation means xz belongs to the relation. Xz will belong to the relation because x is equal to z, and because of this condition it will belong. Okay, so here transitive holds. Let us look at this. X is equal to y, so xy belongs and y minus z belongs, right? Then x equal to x minus z will belong, right, to the relation. Here this belongs, x minus y and yz belongs, right? Then x minus z will belong because of this condition, right? X minus z. Here also x minus z, because of this condition it will belong. Similarly, this x minus y belongs and y minus z belongs to the relation. Okay. Y minus z is equal to minus y z. So x minus y and minus y z belongs to the relation means x is equal to y. So because of this condition x z will belong. So with these 4 different conditions we have seen that these 4 cases are only possible, right? So there are no other cases possible. So with these 4 cases we have seen that this relation is indeed transitive. Alright. So this relation satisfies reflexive, symmetric and transitive property. Alright. So because of that we know this relation is what this relation is? An equivalence relation. Okay. Let us now look at another example. Okay. Let us say this is the relation I have. This relation R is on the set of, say, real numbers. Alright. Now let us figure out if this belongs to the relation. What does this say? AB, this ordered pair, will belong to the relation if A minus B belongs to the set of integers. This AB will be from the set of real number. Alright. So this relation R is on the set of real number. Now let us try to figure out if all this AA, BB, CC will belong to the relation. Alright. So AA, BB, CC. So A minus A is what? Any A. Take any A from the set of real number. A minus A is equal to 0. And 0 belongs to the set of integers. Right? So all this AA, BB, CC from the set of real number will belong to the relation. Alright, because all this A minus A is equal to 0. So it is reflexive. Is it symmetric? A minus B, okay, say it belongs to the set of this A minus B, say it belongs to the set of integers. So A minus B is an integer. Let us say it is equal to I. I is an integer, right? Then B minus A will be minus 1, correct? And if I is an integer, then minus I will also be an integer. So if A minus B is an integer, then B minus A will also be an integer. That means if AB is in the relation, then BA will also be in the relation. Alright. So because of that we know this relation is symmetric. Now let us figure out if this is transitive. Okay. So if AB belongs to the relation, that means A minus B is some integer, right? If BC belongs to the relation, then B minus C is some integer. So if AB and BC belongs to the relation, that means A minus B and B minus C, both of them are integers. Alright. If both of them are integers, then AB and BC, they will belong to the relation. Being transitive means A minus C should also belong to the relation. That means A minus C should also be a integer. If A minus C is an integer, then AC will belong to the relation. So AB belongs to the relation, BC belongs to the relation. The question is, does AC belong to the relation? I can do this, right? I can add B and subtract B, or I can subtract B and add B. Right? I have subtracted B and I have added B to the original equation. Alright. So I am doing this. A minus B, I know it's an integer. Okay, some integer. Plus B minus C, I know it's some integer. So it's an integer plus integer. Integer plus integer will give me an integer. Alright. So I have seen that A minus C is also an integer. Alright. So if A minus B is an integer, B minus C is an integer, that means AB belongs to the relation and BC belongs to the relation, then AC will also belong to the relation. That is, A minus C is also an integer. So if AB belongs and BC belongs, then AC belongs. That means that this relation is transitive. Alright. So that is how we have seen that this relation R on the set of real number is a equivalence relation. Alright. It is reflexive, symmetric and transitive. Alright. Now let us look at one more example. Okay. Okay. So AB will belong to the relation if A is equal to B mod M. So A is equal to B mod M means A minus B is divisible by M. Okay. So that is given by the definition of mod M. So let us try to figure out if this relation on the set of integers is a equivalence relation. Alright, so is it reflexive? All this a minus a, okay, a minus a, b minus b, c minus c is 0. So is a minus a divisible by m? So m is some positive integer. Alright, so a minus a is divisible by m. Yes, 0 is divisible by any positive integer. So it is reflexive. Is it symmetric? So that is the question. Say a minus b. Okay. Say AB is in the relation. We have to figure out if BA is in the relation. Okay. If AB is in the relation, means BA is also in the relation, then it is symmetric. So let us say AB is in the relation. AB is in the relation means what? AB is perfectly divisible by M. That means if AB is perfectly divisible by M, and let us say when I divide A minus B is perfectly divisible by M. Say when I divide A minus B by M, I am getting the quotient K. Okay, that means A minus B is equal to K into M. Okay, there must be some K where K is an integer, alright, such that A minus B divided by M is equal to K. Okay, in that case, A minus B is perfectly divisible by M. Okay, now A minus B divisible by M with the quotient K means B minus A when I divide by M will give me minus K. That means B minus A is equal to minus K into M. If A minus B is equal to K into M, B minus A is equal to minus K into M. That means if A minus B is divisible by M, then B minus A is divisible by M. Alright. So AB being in the relation implies that BA is also in the relation. Okay. So that is how we know this is symmetric. Okay. Next, let us try to figure out if it is transitive. Let us say AB is in the relation. Okay. And AB is in the relation means what? A minus B is divisible by M. So let us say A minus B, when I divide by M, I get K. So A minus B is equal to K into M. Right? This is from basics of arithmetic, high school arithmetic. Then let us say B minus C is also divisible by M. And let us say this is J into M. Alright? So my question is, if AB and BC is divisible by M, that means AB is in the relation, BC is in the relation. Is AC in the relation? So let us try to figure out. Once again, let me subtract B and add B to the equation, will not matter. Then A minus B is what? A minus B is equal to Km. B minus C is what? B minus C is equal to Jm. So I can take M as common. So what do I see in here? I see A minus C. When I divide by M, I will get K plus J, where K and J are both integers. So this is also an integer, K plus J. Alright. So A minus C is equal to K plus J into M. That means A minus C is also perfectly divisible by M. So what have I seen here? I have seen that if AB is in the relation and BC is in the relation, then AC is also in the relation. Okay. So that means this is transitive. Alright. So this is also a equivalence relation. Okay. Next, let us look at one more example. AB such that A divides B. Okay. So, is it reflexive? So, 1 divides 1. Let us say this is on the set of integers as well. 1 divides 1, 2 divides 2, 3 divides 3. So, all this 1, 1, 2, 2, 3, 3, they will be in the relation. Alright. So, AB being 1, 1, 2, 2, 3, 3, all this A will be in the relation because A divides A. Is it symmetric? Say 2 divides 4. So 2, 4 will be in the relation, right? So when I divide 4 by 2, I get 2. So 2, 4 is in the relation. Is 4, 2 in the relation? Does 4 divide 2? That is the question. 4 does not divide 2, right? So when I divide 2 by 4, I get half. So 4 does not divide 2 perfectly. So 2, 4 is in the relation, but 4, 2 is not in the relation. That means this is not symmetric. Okay? Now I don't need to proceed anymore. Is it transitive? Yes, it might be transitive. It is transitive, but I don't need to care about it. Alright. I have seen that it is not symmetric. So that is how I know this relation is not what? This relation is not a equivalence relation. Alright. Now let us look at this. AB will belong to the relation if A minus B, this mod of A minus B is less than 1. Okay. So is it reflexive? All this A minus A, okay, all this A minus A, B minus B, C minus C is equal to 0. Once again, let us say this is on the set of integers. Alright. So all this A minus A is equal to 0. So 0 is less than 1. Correct? So all this A minus A, B, B, C, C, all of this will belong to the relation. So this is reflexive. Is it symmetric? So I know if AB belong, that means A minus B, mod of A minus B, alright, is less than 1. But I know A minus B mod means B minus A. These two are equal. Right? So mod of A minus B is equal to mod of B minus A. So if A minus B is less than 1, then B minus A is also less than 1. That means if AB belongs to the relation, then BA should also belong to the relation, since they are equal. Okay, therefore both of them will be less than 1. So if A minus B mod is less than 1, then B minus A mod is also less than 1. So if AB is in the relation, then BA is also in the relation. So that is how I know this is symmetric. Is it transitive? Let us try to figure out. Let us say I have A minus B. A is 2.8 minus 1.9, say. Okay, this is equal to what? 0.9. And let us say 1.9 minus 1.1. This is equal to 0.8. Alright. So this 2.8, 1.9 will belong to the relation. This 1.9, 1.1 will belong to the relation. My question is, if it is transitive, then this is A, this is B, this is B, this is C. AB, BC. Then AC, 2.8, 1.1. Does it belong to the relation? Okay, this is the question that I have. Does it belong or does it not belong? What? 2.8 minus 1.1. Okay, the mod of this is equal to what? This is equal to 1.7. Okay, is 1.7 less than 1? No, 1.7 is not less than 1. Therefore, this 2.8, 1.1 will not belong to the relation. Alright. So what have we seen till now? AB belongs to the relation, BC belongs to the relation, but AC does not belong to the relation. Okay. So that is how I know that this relation is not transitive. Alright. So it is reflexive, it is symmetric, but it is not transitive. So this is how I know that this relation R on the set of integers is not an equivalence relation. Alright. So these are a few examples we have seen. This is how we figure out. We first have to see whether it's a reflexive relation, whether it's symmetric, and whether it's transitive. If these three properties are satisfied, then we will know that the relation that we are talking about, it's a equivalence relation. All right, relatively simple. Okay. Now, next let us look at a topic called equivalence class. Okay. Before I talk about equivalence class, I want to just try to explain what equivalence class is, and then we will be looking at the definition. All right. So what have we seen till now? We have seen that say I have a relation. Okay, let me explain this with a relation. I have this relation, say R, and it will contain this ordered pair AB such that this relation R is on the set of all bit strings longer than 3 characters. Okay, uh, set of all bit string with length greater or equal to 3. Okay, so equal to 3 character or longer than 3 character. So it will contain this all this bit string AB such that the first 3 characters of A and B are same. Okay, this is my relation. This is the relation on R. What? R is a relation on set of all bit strings with length greater than or equal to 3. That means this set will contain all 111, let's say 000, 1110, okay, 1111, then 1010, and so on. All the possible combinations of strings that are greater than or equal to length 3 or greater than 3. These are 4, these are 3, some might be 5, 6, and up to infinity. Alright. So here is the thing. What will be in the relation? These two will be in the relation. 111, 1110 will belong to the relation. Correct? Why? Because the first 3 characters of 111 and 1110 are the same. This 111, 111, right? Similarly, 111, 11101 will belong to the relation, right? And then I will have more things in the relation, say 111, then 111001. This will also belong to the relation. Okay. So we have seen with this 111. Okay, we have taken this element 111, and I know this 111 and this belongs to the relation 111, and this belongs to the relation 111, and this belongs to the relation. Here is my question. Let us say I have taken these two. Okay, and my question is, does this pair 1110 1101, does it belong to the relation? 1110 1101, does it belong to the relation? Of course it belongs to the relation. I can see that the first 3 characters of this and first 3 characters of this are the same. Okay, that is the definition of things being in the relation are. So given by this definition. Alright, the first 3 characters of A and B are same. The first 3 characters of this A and this B are same. Alright, so this will also belong to the relation. Alright, so when I have this 111 and something else, then this will also belong to the relation. Alright, now what is the reason for that? What I am saying is this, AB. Okay, now forget this specific relation and think about any general equivalence relation. If AB belongs to the relation and AC belongs to the relation, then does BC belong to the relation? I am saying yes, and let me tell you how. AB belongs to the relation, right? And it's an equivalence relation. Since it's an equivalence relation, therefore it is symmetric. That means BA also belongs to the relation. Correct? AB belongs to the relation and it's a symmetric relation, therefore BA should also belong to the relation. Now BA belongs to the relation, AC belongs to the relation, alright, and it's a equivalence relation, therefore it is transitive. BA belongs, AC belongs, so BC should also belong to the relation. Alright, so same logic, this belongs to the relation, therefore this should also belong to the relation. Alright, so that is something that we have seen. Now what did we see? In the final example, we saw that A was equivalent to B and A was equivalent to C. Then we saw that B was also equivalent to C. Okay. So in other words, what I am trying to stress here is that if A is equivalent to something, okay, then all the things that A is equivalent to will be equivalent with each other. Alright. So let us look at the definition of what is equivalence class. Okay. This is how it is written. Okay. So this equivalence class given by this A. Okay. So A, all the things that are related to A. Okay. If S is some element in the set that is related to A, then we say A and S are equivalent. That we say in the very beginning of this video, right? If AB belongs to the relation R and R is an equivalent relation, then A and B are equivalent. Alright. So if A and S are equivalent, all these things that are equivalent to A will belong to this equivalent class. Okay. This is also a set, and all the things that are equivalent to A will belong to the that set. Okay, and that set is called the equivalent class of A. Now here is something else. This thing A, okay, let us say in this set I have A, B, C. Okay, then I have written A over here. This is the representative of this set. Okay, I can very well write B, not a problem. So the element that I choose to represent this class is called the representative of this class. Alright, in my case I had written A. Okay, not a problem. All of them are equivalent. Right? So A is equivalent to B, A is equivalent to C, and we have also seen that B should also be equivalent to C in this case. If A is equivalent to B and A is equivalent to C, then B is equivalent to C. We have just seen this, we have just proven this. Alright. Now, if we are talking about multiple relation, then this subscript indicating which relation we are talking about should be written. If we are talking only about one relation, okay, say we are talking only about R in our example, then there is no need to write this subscript. Alright. Okay. So let us say I have this set relation AB such that A is equal to B mod 4. Okay. So this is a relation that I have. Okay. Now what are the different equivalence classes given by this relation? That is something that we have to figure out. Let us say I want to figure out the equivalence class represented by this 0. What will I have? I will have 0, I will have 4, I will have 8, I will have 12 and so on. In this direction also I will have -4, -8 and so on. Alright. So these are all the equivalent elements. Why? Because 4 minus 0 is divisible by 4. Okay. 8 minus 4 is divisible by 4. Okay. So -4 minus 8 is divisible by 4. Okay. -4 minus 0 is -4 divisible by 4. So all these are equivalent. Okay. So all these are equivalent in the sense that they are, take any two from this set, that pair will belong to this relation. Alright. So all these are equivalent. Now let us say I have the equivalent class of 1. Okay. I will have 1 over here. I will have 5. I will have 9. I will have 13. In this direction I will have -3. I will have -7 and so on. Alright. Here pick any 3, any 2. 5 minus 1, it will be divisible by 4. 9 minus 1, 8 is divisible by 4. Take -3 minus 1. Alright, -3 minus 1 is -4. It is divisible by 4. So all these elements in this set, you pick any two, okay, that will belong to the relation. I picked 1, -3 minus 1, correct. If I do 1 minus -3, it is equal to 4. 4 is divisible by 4. So pick any two elements from this set, alright, in any order, okay, it will belong to the relation. Alright. So this is one more equivalence class. This is one equivalence class. Alright. These are examples of equivalence class. Alright. Now let us go back to that example. A equal to B or A equal to -B. What will be in the equivalence class of 1? What will be in the equivalence class of 2? What will be in the equivalence class of 5? And what will be in the equivalence class of 0? Think about it. 1 is related to 1 and 1 is related to -1. -1 is related to -1 and -1 is related to 1. So what are all the elements in this equivalence class? 1 and -1. Okay. Why? 1 minus 1 belongs to the relation. 1 1 belongs to the relation. -1 minus 1 belongs to the relation. -1 1 belongs to the relation. Okay. This will belong because of this condition. This will belong because of this. This will belong because of this, and this will belong because of this. Alright. So what are all the elements over here? 1 and -1. So 1 and -1 will be in the equivalence class of 1. Alright. Then what will be in the equivalence class of 2? In the equivalence class of 2, similarly we will have 2 and -2. Same logic. In the equivalence class of 5, we will have 5 and -5. Same logic. What will be in the equivalence class of 0? 0 is equal to 0 and 0 is equal to -0. -0 once again is 0. Okay. So only 0 will be in the equivalence class of 0. Alright. Alright. Let us look at one more example. Let us look at this example. AB, where A and B are bit string with the first 3 character of A and B are same. So A and B are bit strings of length equal to or greater than 3. Alright. So let us try to find out what will be in the equivalence relation of 1 1 1. Equivalence class of 1 1 1. Okay. See, I could have written R here, But since there is only one relation we are talking about, this R need not be written. Alright. In the equivalence class of 1, 1, 1, I will have 1, 1, 1, of course. Then I will have 1, 1, 1, 0. I will have 1, 1, 1, 1. I will have 1, 1, 1, 0, 0. I will have 1, 1, 1, 0, 1. 1, 1, 1, 1, 0. 1, 1, 1, 1, 1, and so on. Alright. So this is the equivalence class of 1, 1, 1. So instead of writing 1, 1, 1, this is the representative, right? I have chosen this element as the representative of this set. It is not necessary that I have to choose 1, 1, 1 only. I could have chosen 1, 1, 1, 0 as well. Not a problem. I had chosen this. Alright. So this is what we have. This is an equivalence class. Now we can find another equivalence class, say with 1, 1, 0. So this will contain 1, 1, 0, 1, 1, 0, 1, 0, 0, say 1, 1, 0, 1, 1, 1, 0, 0, 0, and so on. Alright. So yeah, this is about equivalence class. Alright. So if I give you some relation, okay, and you first have to figure out whether this is a equivalence relation. Alright, so that you will figure out by finding whether it is reflexive, whether it is symmetric, and whether it is transitive. If all these three conditions are satisfied, then you will know that it's a equivalence relation. Next, after finding out whether it's a equivalence relation, then if I give you some element, okay, some element A, and I ask you to find the equivalence class of A, then what will you do? You will find out all the elements that are in this relation that are equivalent to A. Alright, so A, B, A, C, A, D, all these things, if they belong to the relation, then A, B, C, D, that will make this equivalence class. Alright. Yeah. So I hope you got till now how to find the equivalence class represented by some representative. Okay, this element that I used to represent this class is called representative. I could have chosen anything from over here. Alright. So this 1, 1, 1 is equal to this is equal to this is equal to this, and so on. All of them are equal to each other. So all the things that are equivalent to each other, not equal, equivalent to each other, together forms a class, and that is called a equivalence class. Alright. Simple. You refer to the book, solve a few problems on your own, and you will see that this actually is a very simple topic. Alright. Okay. Now before I proceed to the next topic, I want to go back and talk about equivalence, logical equivalence. If say I have three statements A, B and C, okay, and I want to show that they are equivalent to one another, okay, this logical equivalent statements are equivalent to one another, I will show that A implies B, B implies C, and C implies A. Okay, so if I show that A implies B, B implies C, and C implies A, then that is showing that the three statements are equal to one another. Alright, so remember this rule. And this is a topic from unit 3, back when we talked about logical equivalences. So if there are three logical propositions, and I want to show that the three propositions are equivalent, then I can show that the first proposition is equal to the first proposition implies the second proposition implies the third, and the third implies the first. Okay, that would be showing that the three propositions are equivalent. Alright. So with that, let us look at a theorem. So I have three statements over here, 1, 2 and 3. Okay, one says AB belongs to the relation, okay, where R is a equivalence relation. Remember that it's not some random relation, it's a equivalence relation. So AB belongs to the some equivalence relation R. Saying this is equivalent as saying that the equivalence class of A and B are the same, and saying this as equivalent to saying that the equivalence class of A and B, the intersection of these two is not phi, is not empty. Okay, we will show this using this technique that we just talked about. I will show that A implies B and B implies C. Okay, how will I show that this implies this? I will show this using how will I show equality? I will show that if this is true, then A is a subset of B and B is a subset of A. Right? These are sets, of course. And if this set is a subset of this and this is a subset of this, then we will know that these two are equal. Okay. So we will start by this proof. I hope you have noted this down. Let me erase and start proving. Or let me write down the statement. Okay. A or B. Second statement was A is equal to B. Equivalence class of A is equal to B. Third statement was equivalence class of A intersection equivalence class of B is not equal to empty set. Alright. Now let us suppose, okay, some C belongs to equivalence class of A. Okay. So what does this mean? This means that AC, this ordered pair AC belongs to R. Okay. So this is one way of writing this thing. This is another way of writing this thing. ARB means AB belongs to R. Okay. So C belongs to A means ARC belongs to this A. Okay. Next, we know from this that AB, ARB. Okay, we are going to show this implies this, so we know this is true, and then we have supposed that that some C belongs to A. We have to show that this C belongs to B. Okay, how am I going to show this? All right. Okay, so A, B belongs to the relation, right? And this relation R is what? This is a equivalence relation. Therefore, it is symmetric. And because it is symmetric, I know this belongs to the relation. Okay? Okay. Since this is true, we got this from here. We are trying to show A implies 1 implies 2. So we are assuming from 1 that 1 is true. Okay. And this is some supposition. Okay. So we have supposed that C belongs to A. That means ARC, AC is in the relation. Okay. Now AC is in the relation and BA is in the relation. That means BA and AC. Okay. This BA belongs to the relation and AC belongs to the relation. So what is this relation? This relation is an equivalence relation. Therefore, this relation is also transitive. Okay. So therefore, I know this BA and AC belongs to the relation means BC belongs to the relation. Okay. So what do I know till now? I know that this is also true. Okay. We started off by assuming that this is true, and then we have shown that this is true. So what have we shown? This supposition that C belongs to A implies that C belongs to A means C is equivalent to A. Okay, C is equivalent to A. That is what being in this AC being in this equivalence relation means A is equivalent to C. So C is equivalent to A, and we have shown that C is also equivalent to B. This means that C is in the equivalent class of B. Okay. So that is something that we have shown. That if C belongs to this equivalence class of A, means C belongs to the equivalence class of B. Okay. So we have shown that A is a subset of B. Okay. If something belongs to A, then that thing belongs to B. Okay. That is the definition of subset. So we have shown using some very basic assumption that C belongs to A, and that would mean that this is true, and this is of course true because we have trying to show that P implies Q. We will of course assume that P is true. Okay, so we have taken this to be true. Then since this is a equivalence relation, so symmetry is there. This relation is symmetric. So if AB is true, then BA should also be true. And from this two, because the relation is equivalence, therefore it is transitive. So using these two, we have shown that BC also belongs to the relation. That means B is equivalent to C. That means C is in the equivalence class of B. Okay. So we have shown that if some C is in the equivalence class of A, then the C is in the equivalence class of B. So something being in A implies that thing is in B. This is the definition of A being a subset of B. Okay. So this is how we have shown that A is a subset of B. Similarly, using the very same logic, we can show that B is a subset of A. Okay. So that is how we have shown that 1 implies 2. Let us now go ahead and try to see if we can show that 2 implies 3. Okay. A is equal to B. Alright. Now, since A is equal to B, so both of them should contain equal number of elements. Now what will A contain? This AA will belong to the equivalence class of A. Why? Because the relation is what? Is reflexive. It's an equivalence relation, it's symmetric, reflexive and transitive. It is reflexive. Since it is reflexive, so AA must belong to the equivalence class of A. Okay, must belong to this equivalence class. So this element A is in the equivalence class of A, that I know for sure. And it should also be in the equivalence class of B. Why? Because both of them, this set are equal. So this element A, sorry, not AA, A should belong to the equivalence class of A. Okay. And because A is equal to B, A should belong to the equivalence class of B. Alright. Now, I know this element A is common between these two sets. Okay. These two classes. These are sets, of course. So, there is some element A that is common between these two sets. Alright. So, because of that, we know the intersection of these two sets is not empty. It's going to be at least this element. Okay. So that is how we have shown that 2 implies 3. Okay. A belongs to A belongs to B. Therefore, this A intersection B is not 5. It's not empty. Okay. So we know at least there is one element that is common between these two. Okay, therefore it is not empty. Now let us try to show that 3 implies 1. Okay. Okay. This means A intersection B is not equal to 5. That means what? There exists some C such that C belongs to A and C belongs to B. Okay. Since the intersection of these two set, okay, I am calling this set, they are equivalence class, they are sets. From the definition of equivalence class we know it's a set. So these two set, the intersection of these two set is not empty. That means what? That means there is some element C such that C belongs to both of them. Okay. So let us say there is this C that belongs to A and this C belongs to B. What does this mean? This means that C R A and C R B is true. That means there is some CA and CB that belongs to this relation. Alright. Now, what do I know? This CRA belongs to the relation. Okay, what kind of relation is this? This is a equivalence relation. Therefore, this is symmetric. Therefore, ARC must also belong to the relation. Okay. Now, ARC belongs to the relation and CRB belongs to the relation. This is a equivalence relation. Therefore, it is also transitive. So, what do I know? ARB belongs to the relation. AB belongs to the relation. This ARC is true. CRB is true. Therefore, ARB is also true. That means AC belongs to the relation. CB belongs to the relation. The relation is transitive. Therefore, AB also belongs to the relation. Alright. So, that is how we have shown that 3 implies 1. Alright. So, we have shown 1 implies 2, 2 implies 3 and 3 implies 1. So, that is how we have shown that the 3 statements, they are equal. Okay. Okay. Now, before we proceed to the next topic, I want to define one thing. It is the partition of a set. Okay. A partition of a set is a collection of disjoint subsets. Set A, say, subsets whose union is A. Okay. So let me show this with an example. Let us say I had this set A and it contained 1, 2, 3, 4, 5, 6. Okay. Then say A1, A2, A3. Okay. Say is this set, and A3 is this. Okay. What is partition? A partition of a set A is a collection of disjoint subsets, alright, whose union is A. So, I have some set, the partition of the set, these 3 are disjoint subsets. These 3 are subsets of A, okay, and they are disjoint. Disjoint means they do not share among them. Pick any two, they will not share any element common between them. So pick any two over here, their intersection will be the empty set phi. Alright. So you can see 1, 2, 3 is here. None of them are in any other set. This 4, 5 is here. This 4, 5 is in no other set. This 6 is here. 6 is in no other set. Alright. So I have these subsets of this original set. Alright. And when I union these subsets, I will get back my original set. So when I union them, I will get 1, 2, 3, 4, 5, 6. And that will give me my original set. So what is partition? I take the original set and I divide it into different subsets, and all these different subsets will not share any common element. Alright. And when I union all these different subsets, I will get back my original set. So all the elements of this original set should be divided into different subsets whose union will give me back my original set. So that is partitioning a set. Alright. So once again read the definition. A partition of a set A is a collection of disjoint. Disjoint means no two sets will share any common element. There is no joining. These are separate. Okay, no common element between these different subsets. So a collection of disjoint subsets whose union is A. So all these different subsets, when you union them back, you will get back the original set. So this is called partitioning a set. Right? So alright, this is one simple definition that we saw in the middle. So this was the interval in our movie on equivalence relation. Alright. Okay. So what is the point that I am trying to make? All these different sets, alright, all these different, what kind of set? This equivalence classes, alright. So some relation, let us say, once again let us talk about this relation. This contains AB such that A equal to B mod M, B mod 4. Okay. So we saw the equivalence class of 0. It had -8, -4, 0, 4, 8 and so on. We saw equivalence class of 1. It had -3, -7 and so on. 1, 5, 9 and so on. Alright, we saw already this part. Okay. So we saw these two equivalence classes. What other equivalent class are possible over here? Okay. We will have two equivalence class represented by 2. So this will have 2, this will have 6, this will have 10 and so on in this direction. In this direction I will have -2, then -6 and so on. Right? I will have equivalence class of 3. This will have 3, this will have 7, this will have 11 and so on. In this I will have -1, -5 and so on. Alright. Is there any other equivalence class that is possible? Is 4 possible? No, 4 is not possible. 4 belongs to this equivalence class. Is 5 possible? 5 belongs to this equivalence class. 6 belongs here. 7 belongs here. 8, 9, 10, 11, 12 will belong here. Right? And so on. In the negative side also. 0 belongs here. -1 here. -2, -3, -4, -5, 6, 7, 8. -9 would belong here. Alright. So what is it that is happening? Alright. So these are all the 4 equivalence class that we may have. Alright. And these 4 class will do what? The set that we had. Alright. This R is on the set of integers. So these 4 equivalent classes will partition my entire set of integer into these 4 different classes. Alright. These 4 different subsets of the set of integers. Now think about it. Take any integer, it will belong to one of these 4 classes. Alright, so when I union these 4 classes, I will get back my set of integers, and then these are all disjoint in the sense that there is no integer which will belong to 2 of these classes. Alright, so when I take any integer, when I divide it by 4, I will get one of these 4 remainders. I will not get 2 different remainders. So that integer will belong to the whatever remainder it is being pointed to, it will belong to that class, right? So this is what I have. My entire set of integers, alright, say this is my set of integer. It is now partitioned into 4 parts. This one is represented by 0, another represented by 1, another represented by 2, another represented by 3. Alright, so when I union all these 3 together, all these 4 classes together, I will get back my original set. Okay, that is the set of integer that I was working on. So yeah, this is the thing. So what is happening here? If say I have some relation, okay, some equivalent relation on some set A, then all the different equivalent classes, they will partition my entire set A. Okay, and then when I union all of them, I will get back my original set. So that is what partition means. But point to remember here is that all these different equivalent classes will partition my entire set. Okay, it will divide my entire set into different subsets, and these subsets will not have any common element between them. Okay, all this will be disjoint, and when I union them, I will get back my original set. Let us look at this with another example. Okay. So A and B. So this relation R is on the set of all bit string of length equal to or greater than 3, like we were doing. So what will be in the relation? All this AB such that the first 3 characters of A and B are same. So how many equivalence classes might be there? Think about it. 0, 0, 0 will represent one equivalence class. 0, 0, 1 will represent one. 0, 1, 0. 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0. And 1, 1, 1. So this will contain all these strings 0, 0, 0, then 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, and so on. This will contain say all the strings 0, 1, 0, then 0, 1, 0, 1, 0, 1, 0, 0 and 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, and so on, right? And this will contain all this 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, and so on. Alright, and similarly we will have all these other equivalence classes. Alright, now what will happen? All the bit string that starts with 0, 0, 0 belongs to this equivalence class. All the bit string that starts with 0, 0, 1 will belong to this equivalence class. All those that start with 0, 1, 0 will belong to this, and so on. All those that start with 1, 1, 1 will belong to this class. Alright, so what will all these different classes together do? I have 8 classes over here. Okay, these 8 classes, they are disjoint. So a string will belong to one of these sets. Okay, a string will have three characters. First three character, they cannot be different, right? A string cannot begin with 010 and 011. Okay, it will either begin with 010 or it will begin with 011 or anything else. It cannot begin with two different things. Alright, so a string will belong to any one of them. A string cannot belong to two different of these sets. Alright, so we know all these classes, all these sets, they are disjoint. Okay, they do not share any element. And also, when I union all these 8 classes, what will I get back? I will get back my original set of all bit string with length 3 or greater than 3. Alright, so I have done what? Using these equivalence classes, I have partitioned my original set. Right? So I have partitioned my original set into disjoint set whose union will get me back my original set. So that is what the partitioning does. Okay. Now, in previous example, I have seen that I had partitioned into a 4 different equivalence classes. Here I have partitioned into 8 different equivalence classes, but it is not necessary that all of them will be some finite number. Okay. Let us look at this relation on the set of integer a is equal to b or a is equal to minus b. We had seen that the equivalence class of 0 contains only 0. Equivalence class of 1 contains 1 and minus 1. Equivalence class of 2 contains 2 and minus 2. Okay, and this will go on. Okay, so all these infinite sets over here, countably infinite set, when I union them back, I will get back my set of integers. Alright, so this is one more example of partitioning using equivalence class. So the thing that I am trying to point out once again is this, in this part, that when I have this equivalence class, okay, on some equivalent relation, so some equivalent relation will have a certain number of equivalence classes. So all these equivalent classes, they will be disjoint. Okay, so all the elements that are equivalent to 1 will belong to this set. All the elements that are equivalent to 2 will belong to this set. 1 and 2 are not equivalent. If 1 and 2 are equivalent, then 2 would belong here. Okay, so all these that are equivalent to 2 will be here. All equivalent to 1 will be here, and they will be disjoint always. Okay, all this will be equivalent to each other. All this element in this set will be equivalent to each other. All this element in this set will be equivalent to each other. Okay, equivalent defined by my relation. Alright, so these equivalent sets, these equivalent classes will divide my original set into different subsets, right? And when I union them back, I will get back my original set. So in other words, these equivalent classes will partition my entire set. Alright, so yeah, these are all the examples, alright, and the definitions that we have regarding equivalence relation. So I hope you understood everything. We will of course have more questions in the assignment. Please solve the assignment question. That will reinforce these concepts in your mind and also enable you to practice, and with practice you will know more about how to solve this problem. Okay, I hope you understood everything in this video. If not, then first refer to your book. Okay, your book Discrete Maths and its Application by Kenneth H. Rosen. Everything that we did today is from that book. Okay, and if still you have some confusion, then of course you can WhatsApp me, you can mail me, or you can write your doubt in the comment section below. I am still hoping that you understood everything in this video. If not, then do this thing that I asked you to do. So this ends our video. In the next video we will be looking at a different topic, partial order sets. All right. Relation, partial order relation. So with that, let me end this video. See you in the next video.